Okay. In the last video, we have discussed about the concept of power and few examples, I think example 5.10 and 5.9. Now we are going to discuss about collisions. So to start with, what is collision? What do you mean by collision? Let's say there are two bodies, body A and body B, and they are moving with some velocity. Let's say initial velocity of body A is UA and initial velocity of body B is UB, and they come into direct physical interaction during a very short interval of time. That is, they are hitting each other, they are applying forces on each other. So let's say this is the situation, and this happens for a very short interval of time, delta t. During this time, there will be a force on body A, let's say it is Fa due to B, and at the same moment, there will be a force on body B due to body A. So let's write it FBA. And now, so we can write a formal definition for collision. Two bodies come into direct physical contact, applying forces on each other for a very short interval time. This phenomenon, we can say, collision is happening. Now, as we know, these two forces are equal and opposite, equal in magnitude and opposite in direction. So we can write FAB equals to minus of FBA. And now, what if we are trying to get the effect on their momenta? So, if the change in momentum of body A, let's say PA per unit time, that is divided by delta T, it should be equal to force on body A F due to B, FAB, and the same argument we can continue to body B, where delta PB divided by delta T will be F on B due to A. And we know that this FBA is nothing but minus of FAB, that is equal and opposite, and equal in magnitude and opposite in direction. So we have minus delta P A divided by delta T. So we can write here delta PB equals to minus delta PA, or we can write here delta PA plus delta PB should be equal to 0, and this delta PA, that is change in momentum of body A, and delta PB is change in momentum in body B, is nothing but total change in momentum of the system, and this is coming 0. What does it mean? There is no change in momentum of the system. Here system means the two bodies, means we are talking about a system which includes the body A and the body B. And of course, there is one condition. Let me write it once again. Delta PS is 0. That is, initial momentum of system is equal to final momentum of system. This we call conservation of linear momentum. And one thing I would like to mention here, that there is a condition for this to happen. There is no net external force on the system. Net external force on the system. Now you can get it. So this is law of conservation of linear momentum. If there is no net external force acting on a system, the linear momentum of the system will remain conserved. And this is what happening in this case of collision. Now, making the things simpler. Okay, before that, let's introduce kinetic energy thing here also. What will happen to the kinetic energy? So there are two possibilities. During collision, there is one possibility that kinetic energy of system will not change. And there is another possibility that some non-conservative force may come into action. I mean, some dissipating force may come into action, like friction, and hence the kinetic energy is going to be changed. So, change in kinetic energy will not be zero. In this case, look, one thing is common for both, that linear momentum is not going to be changed, whether it is the kinetic energy changing or not. Here, kinetic energy is not changing or kinetic energy is changing, but the linear momentum is not going to change. Yes, condition is the same, that no net external should be acting on the system. So in this case, this first case, this kind of collision, we call it elastic collision. And here in second case, we call it inelastic collision. Okay. In this second case, inelastic collision, let's start uh, first this case. So in this second case, there is a special case also where there are two bodies. Let's say this is body A and this is body B. And after collision, these two bodies are moving together. Means they got stuck with each other and then they are moving together with a common velocity, common final velocity. Let's say this is V. So let's say initial velocity is UA and final velocity is V, common velocity, and this is UB. Okay. To For this type of collision where these two bodies stick together and move with a common velocity, we call it perfectly inelastic collision or completely inelastic collision. So I can give you a real life example for this. Let's say there is a hanging block. Yes, while doing ballistic test for bullets, there is a hanging block and here bullet is fired, and when this bullet hits this block, it got stranded into it and then these two move together. So this is a real life example for inelastic, perfectly inelastic collision. Now, coming back to the situation. Okay, to keep this all things very simple, we are going to discuss in one dimension only. To start with, we are going to discuss in one dimension. Means these all things are happening along a single line. That is, this body A is moving along this line, and after hitting, these two are moving along a single line, the same line. Okay, now. So what will be happening here? The first thing, the initial momentum and final momentum, these two things should be same. Let's make it more simple and write. Initially, this body is at rest, let's say, for time being. This body comes behind and this body hits body B and they are moving together now. So the first thing is MA UA, that is initial momentum of body A, and plus MB, UB is 0. So initial momentum of body B is going to be 0. So let's not write. So here initial momentum of the system should be equal to the final momentum. And what is the final momentum of the system? This is a common mass here comprising both MA and MB, and this is moving with a final velocity V. So we have final common velocity as MA divided by MA plus MB whole multiplied with UA. This is one thing here. And why I have obtained this equation? Yes, because there may be a situation where you have been asked, uh, if a body is moving with initial velocity something UA, and maybe the other thing may be there, not only UA. So if a body is moving with a initial velocity and then it has some mass, it hits another body at rest, and it is perfectly inelastic collision, what will be the final velocity? So you can obtain the final velocity with this equation. This is a kind of inelastic collision. There will be change in kinetic energy of the system. That is, there will be some final kinetic energy of system minus initial kinetic energy of system, and this thing is not going to be zero. We can find out what is the final kinetic energy of the system. 1 by 2 M1 plus M2. Now the new mass is this, combining the two bodies, and final velocity square and initial kinetic energy. As body 1 is moving and body 2 is at rest, then it will be M1 U1 square. And we have just find out this thing, V, final velocity of these two masses combining together, means that combining together move with a common velocity, and this is the velocity. You can put this instead of here V, and then you will get something. Let me write it directly, you try by yourself, and you can come to a conclusion that delta K of system will be something negative 1 by 2, and then here it should be, I guess, M1 into M2 by M1 plus M2, and then here it will be U1 square, because instead of V, we have less the term containing U1. So you can check it if it is coming or not. But the main thing is here, this final kinetic energy is a negative value here. That sorry, the change in kinetic is negative value here. That is, final kinetic energy is less compared to the initial kinetic energy. There is a loss of kinetic energy, and that loss is due to dissipating force. We are mainly due to friction, and this is initial velocity. So this one we can continue. Okay, so let's move to the next type of collision. We have studied now perfectly inelastic. Now we are moving to elastic collision. Now you may be thinking that why not inelastic collision? Yes, we will come to that part also. But let's start with the simplest one. So now elastic collisions, and this is in one dimension. Yes, that's simplest. Okay, in case of elastic collision, this momentum change of system is zero, and this kinetic energy change is also zero. So let's say there is a body of mass M1 with initial velocity U1, and another body of mass M2, initial velocity, let's say, zero again. Simplest one. So what will be the momentum conservation here? Initial momentum M1 U1 plus M2 U2 will be zero, so you need to write it. And the final, let's say after collision, their masses are not going to be changed, but the velocities are V1, and it also gains some velocity, final V2. So that will be M1 V1 plus M2 V2. And about kinetic energy, so initial kinetic energy of the system will be M1 U1 square divided by 2, and plus 0, because this body is at rest, equals to M1 V1 square by 2 plus half of M2 V2 square. Now we have two equations and two variables. Why I'm saying two variables? Only because we are considering that we know the masses M1 and M2, and we know the initial velocity of this body, first body U1, and U2 is 0, that is known. So we have to find out what is V1 here in terms of M1, M2, and U1, and what is V2 here in terms of M1, M2, and V1. So we have to further proceed with these two equations. We have two equations, two variables. Obviously, we are going to solve it and get the expression for V1 and V2. Okay, now let me rearrange these terms in a more simpler way. In a more simple way. So N1 U1 equals to N1 V1 plus N2 V2. And here 1 by 2 N1 U1 square, we can just
take this 1 by 2 because it is common on both sides. So here we will have n1 v1 square plus n2 v2 square. Okay. So this is equation 1 and this is equation 2. We have two equations and two variables. Two variables are here, means two unknowns. Two unknowns are here, v1 and v2. That is final velocity of body 1 and final velocity of body 2. Now we have to do some calculations and tricks here. So first, I would like to eliminate the term containing n2. For that, I can do one thing. I can multiply here v2 and then from see n1 v1 v2 yes, we should be calculate about that. N1, V1, V2 plus N2, V2 square. Okay. And then this is the same. Let's say this is equation 3. Now we can do one thing. We can just subtract, yes, we can subtract equation 3 from equation 2. So M2 term will be eliminated. So this one will be M1 U1 square and minus this one. M1, U1, V2, and then on the right hand side we will have M1, V1 square minus M1, V1, V2. Okay, and we can rearrange and how can we do N1? Okay, we can eliminate N1 because it is common to each and every term on both sides. So we can just divide both sides by N1 and then we will have U1 square minus U1 V2 equals to v1 square minus v1 dt. And then we can bring this term to other side and this term is so. So we will have u1 square minus v1 square equals to that it should be u1 v2 minus v1 v2. Okay. So u1 v2 minus v1 v2. Okay, it is getting simpler now. You can write u1 plus v1. We can apply s square minus b square is equal to a plus b in here and b that will be b1 here we will find that a plus b is zero times b a square and b square right. And here we can do one thing u1 minus v1 look v2 is common so we can take it out. So from here we can get the final velocity v2 and this one. Okay, you can consider because this two, yes, this quantity is not going to be zero if there is some initial velocity, as we have said earlier, there is some initial velocity, and then this must not be zero unless final velocity is the same. Yeah, for the first body. So for that reason, we can write v2 equals to v1 plus v1. That is final velocity of body 2 is initial velocity plus final velocity of body 1. So, and of course, you can write it in terms of vectors also. You can write it. Here we are talking about one-dimensional problem. So only plus and minus sign is going to do the work. Otherwise, you can use it. Okay, soon we are going to discuss it about in two dimension also. There we will be more process about vector science. So let's continue. Now we have got a final velocity of body 2. From here we can get final velocity of body 1 also. Yes, of course we can get using these two equations and this one. And now I'm writing directly what is the initial velocity and final velocity of these two bodies. And this is equation third, I think. And earlier we had two equations here. And where is, okay, fourth. It was correct, equation 4. Okay, so here we have equation 1 and equation 2. From here, if we put that V2 here, we will get V1. And from V1, again, if we get V1 from here, we can get V2. Okay, so in terms of, let's write here V1 and then V2, final velocity of body 1 and final velocity of body 2. So here we have V2, we can put this V2 here and you can do it by yourself. After doing all these things, you can get V1 and V2. I'm writing directly. You try by yourself and try to get the result and check whether it is the same or it is coming a different one. Okay, so let's continue. Finally, we have these two things. V1 equals to m1 minus m2 divided by m1 plus m2. U1, which is initial velocity of body 1, and m1, m2 we know already. They are the masses of body 1 and body 2 respectively. And here final velocity of body 2, 2m1 divided by m1 plus m2 and whole thing multiplied with initial velocity of body 1. Now, I would like to mention three different cases here. So, number one, if m1 is equal to m2, that means these two bodies are of same masses. So what will be happening here? So let's say this is coming with U1 and yes, striking with this body, which is at rest. So what will happen? If M1 equals to M2, then V1 will be 0. That is final velocity of body 1 will be 0. That is body 1 will stop after collision, and the final velocity of body 2, if M1 equals to M2, you can write here M1 instead of M2, then it will be 2M1, and 2M1 divided by 2M1 will give you 1. So V2 equals to U1. So based on these two arguments, we can say if these two masses are equal, this first body hits and stays there, and then the second body continues with the velocity as it was U1 for the first body. Now the U1 velocity will be imparted to the second body. Now, second case, if M2 is much greater than M1. So coming back to this point, M2 is greater than M1. What will happen? Let's say M2 minus M1 will be something minus of M2. If let's say this is something 0.1 gram and this body is something 10 kg, means nearly 10,000 gram. So this will give you approximately, not exactly, but approximately you can say this is minus 10,000 gram. Okay, this is minus sign. Here you have 10,000 gram. So ultimately, this will be minus M2. And with the same argument, you can say if M2 is much more greater than M1, this you can write approximately M2. So minus M2 divided by M2 will give you minus 1, and then you will have V1 equals to minus U1. What does it mean? Physically, it is representing a situation where this M2 second body is much more heavier compared to this body. So this is going to hit this M2 with some initial velocity U1, and then it will return with some final velocity, and this final velocity is equal to minus U1, means this final velocity will be equal in magnitude but just opposite in direction. And what about the motion of this body, this M2? What will be its final velocity? V2. Let's check from here, and it should be giving the same result as we can guess here, because this body M2 is not going to move at all. So maybe there is a little movement, but roughly we can say this body is not going to move at all. So this M2 is much more greater than M1. So this thing you can write nearly M2, and M1 by M2 is very a small quantity. So you can say this is nearly M1 by M2 is very a small quantity. That is, you can say this is nearly 0. And in that case, you can say V2 is nearly 0. This is one thing. And you can guess here, if this body is much more bigger and heavier, this is going to hit and return back, but this body is not going to move apparently. Now, coming to the third case here, what is the third case? If M1 is much more bigger and heavier than, not exactly bigger, but it should be heavier. So if M1 is much more heavier, means the first body is much more heavier compared to the second one. So what will be the motion after collision? So let's get back to these two equations. So let me clean it up, then we can continue our argument. So M1 is much more greater than M2. It means M1 minus M2 is nearly going to be equal to M1. So you can write this thing, okay, okay. So you can write this thing is going to be nearly M1 divided by M1. Yes, M1 plus M2, you can also say this is nearly equal to M1. M1 minus M2, you can say this is nearly M1. Okay, because this M2 is negligible compared to M1. So this is a kind of approximation you can say. Okay, if you go in minute details, there will be very fraction means very less things coming up, but here we are going to just approximate. So it will be 1. So this V1, final velocity of body 1, is going to be nearly initial velocity of body 1. What does it mean? It means if this body is much more heavier, after collision, it is going to continue. After collision, this first body is going to continue with the same velocity. Its final velocity will be in the same direction and the magnitude will be the same at it was earlier. And what about the second one? So here you can put that thing. This is a kind of rough approximation. So if you are going to calculate with exact values, even if it is much more bigger, still you are going to get some fraction. But yeah, we are taking approximate values, and then to make the things and our discussion simple, this second case means V2, final velocity of body 2 is going to be, you can write this is 2m1 and this is m1 plus m2. M1 plus m2 you can write nearly m1. So this will be twice of u1. And look here, there is no negative sign. So you can say the second body is going to move with the velocity v2 in the same direction as the direction the first body was moving, or after collision is moving, and with twice of that velocity. So up to here, I guess it will be okay. And in case you have any doubt, you can put it in comment section. And yes, up to here, all good, all fine. In the next class, in the next video, we are going to discuss an example where we will be more clear about the concept of this collision, especially in one dimension. And yes, we are going to generalize the things. Earlier, we have kept the second body at rest, but in the subsequent sections, in the subsequent videos, we are going to discuss in general. But before that, we are going to discuss elastic collision in two dimensions. Okay, so see you.